Got an interesting antique here called a slide wire rheostat. And it's going to really help us understand the relationship between the energy per charge, or the voltage, and how fast that charge flows through the circuit, the current. And what a slide wire rheostat is a big coil of wire, and it's wrapped around this drum. And then there's this thing here that can slide on it, which is called the wiper. So it can just kind of go up and down. There's three places you can hook electricity up to flow through. You could hook electricity up here and here, in which case it might go through the entire coil of wire. But you could also hook it up between here and here. The connection for that is this right here, because this is hooked up through metal. And the reason you would do that is because it makes a connection with the coil of wire there. The path of electricity through would be here, around the coil, and then up through this and out. And by sliding this, that means I can actually change the length of the wire that stuff has to go through. So let's see if we can use that to figure out some relationships between voltage, energy per charge, and then current, the speed of charge. So I'm going to build this circuit here. I'm going to put 25 volts across this rheostat. I'm not going to hook up this end at all. I'm leaving it bare. And I'm going to hook the wiper up to the negative of the power supply, and I'm going to hook the positive up to this end of the coil. I want to put some meters in there too. I've got my voltmeter and my ammeter. So let's remember how they have to go. The voltmeter goes across the circuit. And the ammeter actually has to go in the circuit. So that when I put it together, the electricity is going to flow through part of the rheostat, out the wiper, through the ammeter, and back home. So that'll be the current. All right, let's start putting that together. So we'll start at the positive. So I'll find my positive power supply. And forgive me, this is hard to do one-handed. So there it goes. We're hooked in. And then the current passes through the rheostat, out the wiper, which I think is that connection, and then it goes to the ammeter. So I'll hook the positive wire of my ammeter up to the wiper. And then it goes from the ammeter back to the negative. So I'll find my negative power supply. Just trying to get the, there we go. I'll hook that up here. And as you can see, we instantly got a current. It looks like it is about 0.2 amps. So we got that all set up. Now we need to put the voltmeter across. And as we can see, we end up with 25 volts. So let's try sliding the wiper arm and see what happens to voltage. Whole lot of nothing. No change at all. It stays about 25. Let's watch what happens to current. It's like the closer I get it over there, the more the current goes up. And the more I bring it back in this direction, the current drops. So what's going on there? Well, again, when I have the slider over here, that means electricity has to pass all around this hundreds and hundreds and hundreds of times before it gets to go back to the power supply. And apparently that's slowing down the current. But if I shorten the length of wire, apparently that speeds the current up. So there's something about the wire itself. The more you have to pass through it, the harder it is for electricity to flow. So let's see if we can come up with a law that supports those two observations. So what's going on? Why does changing the length of the wire affect how much current appears to flow? Well, if you remember what current is, it's electrons randomly ping-ponging off atom to atom to atom, but gradually over time drifting in the direction of your circuit. And every time one of these atoms gets hit, it starts moving. And of course, motion of atoms turns into heat. So the longer you have to go through these atoms, the more energy you lose. And that's why we're actually seeing the current drop. The same voltage, the same energy per charge is not all going into making charges flow. It's partly going into moving the atoms. And the more atoms it's got to move, the less energy there is for the charges to flow. So basically, there must be some property that describes how much an electrical device slows down the flow of charge. As we can see in this device, that property gets much bigger. It slows down the flow of charge more when we make the length of wire longer. And that property is called resistance. Resistance is the ability of an electronic device to impede the flow of charge. And as we can see, current is inversely proportional to resistance. I've got the same circuit as before, but I've actually added in a way to control how much energy per charge, how much voltage there is. It's actually just another rheostat, although it looks pretty different. But what's important is what relationship in our circuit there is between volts and amps. So let's watch. Right now, I've got the volts at 20, and the amps are reading about 0.7. Watch what happens as I increase the voltage. Do you see the amps going up? So now the voltage is about 24, and we've gone up to nearly 0.85. So what that tells us is that current is proportional to voltage. Let's see if we can combine those two observations together. So our experimental observations were that current was inversely proportional to resistance and directly proportional to voltage. So if we combine these together, we expect that current should be proportional to voltage over resistance. And it turns out that current is actually equal to voltage over resistance. By knowing how fast charges are flowing versus how much each charge is being pushed, we can always calculate how hard it is to push charges through. Likewise, if we know how hard we're pushing and how hard it is to push, we can calculate current. If we know two of these variables, we can always figure out the third. It's usually written a slightly different way. Voltage is current times resistance. And in this form, it's usually called Ohm's law. So Ohm's law is the relationship between voltage, current, and resistance, which we showed by varying the length of a wire and seeing how that affected resistance.